itself to RDS, which is the registry and the discovery service, which is part of the ISO 4 specification. And that ISO, and then the broadcast controller has the capability to pull all of that information from RDS. So the thing is that it is a publish subscribe method in such a way that the minute a camera is connected, that a camera has been connected. So everything is so automatic once you use ISO 4, 5, and 6, that many of these things are so automated that you no longer need to go and say, oh, I connected a camera, now I need to go to the broadcast controller, look at that GUI there and start to enter some data, and by the way, where did I connect that from? So all of that stuff goes away because everything is so automated. And so the broadcast controller now knows all its endpoints and then can go and inform the network controller or create those endpoints into the network so that the network knows here are the endpoints that I should permit. Now the thing about LLDP is LLDP stands for Link Layer Discovery Protocol. It is a protocol that's been around for what seems like ever. In fact, there was CDP, and some of you may know that. CDP actually predates LLDP by almost half a decade or something. And CDP stands for Cisco Discovery Protocol. So we used to have this protocol a long time back, and eventually it was standardized in IEEE as an LLDP discovery protocol. And the whole idea is it's a layer 2 protocol, and it is only between two devices, and the idea is that it's going to discover these two devices. So we have, as part of the specification, we have kind of required that these entities, these endpoints, be it a camera or a switcher or a monitor or whatever else that is connected to the IP network, support LLDP, because if that is how network switches discover themselves, all the networks, whether irrespective of which manufacturer it's coming from, do support LLDP. So, and all the IP devices, that even things like these phones support, LLDP. So the idea is of these devices that these are some of these very common IP protocols that one expects in an endpoint. So if that is supported, then the network can learn about it, and likewise the endpoint also can learn which switch it's connected to. I'm connected to switch 1 on this interface, on interface, let's say 10. That information is known now to the endpoint, which it then can share, like I said, with eventually with the broadcast controller. So if I think about setting up the network, when we think about setting up the network, and I said a little bit about flow authorization, there are really two parts to that. The first part of it is reserving the bandwidth. It's the part that we say admission control. The entity that wants to set up the network, let's say in this case the broadcast controller, goes to the network and says, okay, I need this. I mean, if I want to set up a flow, it automatically means I need that much of bandwidth to be allocated to that flow, which means reserved, set up resource reservation. The network also has to figure out the path. Now, if we talk about a common topology that we use in the data center is called the spine and leaf. And spine and leaf basically means two layers. You have spine switches which flare down to this leaf node. And that path, the reason is that if you're going to do resource reservation, you have to know exactly which link, which interface it's going to come off and where it's going to go into the spine and so on, because you are going to set aside bandwidth, and you have to be sure there is bandwidth in that spine, in those links, in order to satisfy this flow. So there is a path selection that happens during this process, and then the resources are reserved. Then the second part of it is that, okay, now can I send the bits, the content itself through the wire, which is where the 2110 comes into play. So the resource reservation, the ISO 6, according to ISO 6, it's strictly done through the API. Why? Because it is a authorization, it's a security function. And I always use this example. I don't know if it's a good analogy or not, but if you, let's say you have like a stadium or something, you're not going to let every door kind of issue their own tickets, right? It doesn't quite make sense, because one, you may not even be able to trust the person manning the door, right? But on the other hand, you give that, that responsibility of issuing tickets to enter into that stadium to a central authority. That's what it is all about. So the broadcast controller is that central authority. It decides what can go in this infrastructure, which is the stadium, right? You don't let every camera and every video switcher go and say, oh, I need this bandwidth, because then you really, yes, maybe the video switcher says, I need, so much bandwidth, and it might be using more bandwidth than it really needs to for that time for that particular time. So the resource reservation always is done through the API. It is done from the broadcast controller. That is why if you reflect back to the slide I showed on the architecture, we said that the broadcast controller is the central point. It is the point that, that owns all the policy decisions. Now, with respect to flow routing, there can be two parts. One of it is, as part of that information coming down from the broadcast controller, it can say send that flow from the camera to the switcher. Now, in this, not only the resource reservation happens, but the flow also starts to move, and then eventually you see the video on the video switcher. Or alternatively, what could happen is that you are doing that authorization from the broadcast controller, but your video switcher itself decides to ask for the flow or pull the flow. And that's a very common model in IP network, because in this case we will be using multicast because every flow really goes to more than one destination. Therefore, we would use a multicast protocol, which is called IGMP. In this case, the video switcher will execute an IGMP join. So I'm joining this flow, so give me a copy of that flow. And then when it's done with that flow, it says IGMP leave. So it says no longer send me that flow. So that can happen. And there is a good reason as to why sometimes the endpoints may want to ask for the flow themselves. The reservations will happen by the controller, but the endpoint may actually decide to actually ask for the flow. And this is because the endpoint knows its buffer capacity, knows exactly when the flow has to be switched from flow A1 to flow 2. So it might execute what we would call a join before leave or a leave before join, because sometimes it might want to bring both the flows, the flow that it has to give up and the flow new flow that has to take its role. It might want to bring both so it can do a clean switching, a frame accurate switching. So that is the part where we call join before leave. So you join the second flow before you actually leave. Now, in some functions where maybe frame, for the sake of, because frame accurate switching in this condition will use up twice the amount of bandwidth, right? So maybe in some cases you might not want to do that. Maybe I'm just setting up this production control room and there's these monitors, and maybe they don't need frame accurate switching at that point in time, in which case you might just do a leave before join. You let the flow, the old flow go, and then you start to join the next flow. So that timing of when it asks for the next flow or when it gives up a flow is all known only to that endpoint. I mean, something on the cloud there, like broadcast controller, is not going to really know to execute it exactly at that point in time. It might not even scale. So for that reason, you might want to let that flow routing be the responsibility of the destination devices, and says you go ask for the flow at the time you need it. And that is the reason why there is that split. Even though you have an API, the API does allow for the destination devices to draw its own flow. So that's the split here, right? I mean, some of these, I mean, there's, I'm kind of like going into the weeds or the 100 feet level fairly fast. So if it is sort of confusing, or it says, why am I listening to it, let me know.
Is the flow routing in either or? Do I have to go by API, or can I just implement IGMP?
You could implement IGMP. So you execute the resource reservation through the API, and then you can do IGMP to do the flow routing.
Okay.
Yeah.
And then which version?
This is allowed by ISO 6 API. When you
IGMP version.
Oh, you could use in this if I speak from a perspective of ISO 6, ISO 6 doesn't care. Okay, it is about what network devices you use and what endpoint devices and what you have actually wanted to do in terms of network design. Though I think there has been a strong preference for version 3.
Version
3, yeah. So let's go through this example workflow. I think I might have said pieces of this. I've kind of used my hands to describe how this all works, but let's just see it in a slide. I think that would be a lot more helpful. The first step is, like I said, ISO 4. So when a camera comes online or when a switcher comes online, it sends an ISO 4 register message to this entity called the registry and the discovery service. So it goes and registers itself. It says what it is, and is it a sender or a receiver, and what it can do, what its capabilities are. And one of the other things that can happen is that the broadcast controller can do one of two things. It can constantly query the RDS in order to grab all that information, or it can subscribe itself and says, whenever you get anything new, just let me know. And in that case, the registry and discovery service will publish that information to the broadcast control service. So let me just finish up this line. So theoretically, the way I think of it is that if you have a control panel attached to that broadcast control service, it's really possible for that control panel to just get one more source light up, all because this is all automated. So you don't have to almost enter anything in this. I mean, there's a lot more complexity there, but I'm just trying to explain to you how that ISO4 allows that all these endpoint sources and destinations to be automatically learned with its capabilities in the broadcast controller. You had a question?
What on ISO4, would that be what we have traditionally called a streaming service?
No, I don't think so. Streaming service, I don't really know what streaming service is, but ISO4 is a new piece of work, and I think part of the, I mean, maybe it's true it's the same thing, but I don't know what a streaming service is. But if I think of streaming, I'm thinking of streaming content. This has nothing to do with content. This is more about this is who I am. Yeah, more like if you're somewhat familiar with the IP technologies, this is similar to DHCP about how I get an IP address, right? You say, okay, can you give me an IP address? So it's something similar, but not the same. Or even an endpoint doing 802.1x to authenticate itself. This is kind of similar in that same vein.
So, sorry, I'm just missing the point. Once, say, camera 4 comes live,
Mm-hmm.
and it tells the controller it's there, present now,
Mm-hmm.
does it depend upon a prior reservation for the controller to know where to send it to?
No,
How
the
do you
thing
know
is,
where to send it?
yeah, so the thing that it will have to have some knowledge of where the RDS is, where it's, to some extent, its registry services. And one, that is, there is a protocol for how it learns where the registry service is, and so it sends it to the registry service. And likewise, there is also a learning that happens between the RDS and the broadcast controllers, so they can actually exchange information amongst them. So, and at this point, it doesn't do anything about bandwidth. All it does is really talks about, okay, I'm a camera, this is my MAC address, this is, I'm a sender, receiver, what its capabilities are, and so on.
How do you know, how does it know if it's unique? The unique address, like you mentioned MAC address,
Mm-hmm.
what's the registration number then? Is there an iOS 04 registration number?
So all of these will have to have unique MAC addresses,
So it's MAC
right?
address.
Yeah,
Okay.
but also the registry, I believe, gives it a unique address. I do know on the network side, I mean, I don't work on RDS, but I believe all of these will be uniquely known with a set of pieces of information. And it has an identifier for each of these devices. At that time, let's say you talked about camera 4. Now, camera 4 starts to maybe transmit at that time, right? It came online, it's connected to the IP network. What prevents it from just sending the bits to the IP network? But at that time, nothing actually happens beyond going to that switch that it's connected to, because the switch says, I don't know who you are. I've not been told that you are somebody valid. And now also there are no receivers at that point in time, so I'm just going to keep dropping the packet. So the camera can be transmitting, but it does not go anywhere from the network perspective. So as you can see, the line stops right there. Okay. So the next step is that creating the endpoint, or what I talked about earlier, which is the endpoint registration. This is the part where the broadcast controller says, well, I know it's camera 4. I need to tell the network that there is a camera 4 now. So it tells the network what this device is. And the pieces of information that it gives at this point in time is that it provides it the MAC address. It provides the IP addresses that will be used by that endpoint. And it also provides where it's connected to from the switch perspective. Because of LLDP, the camera 4 has already learned that it is connected to, let's say, switch 2 interface 10. That information is given from the broadcast controller into the network controller. Now, network controller already knows that there is a device connected to switch 1 interface 10. So it can, and it also knows the MAC address. So it will match that information with the information it received and says, yeah, that's right. And so therefore, it is now authorized. So from now on, that source is capable of actually sending or receiving traffic based on whether it's a sender or whether it's been authorized to be a sender or a receiver or both. So that's the part where ISO 6 gets initiated. Now ISO 5, because that's the part where the connection gets made, right? It's all about I'm sending this many flows, this is the multicast address, and all of that thing relating to the media. So think about it as media description, things that has to happen so that the video switcher knows which ones to join. I mean, if I have to join and ask for a flow, then I have to know what that identifier is, and all of that information is exchanged by ISO 5. So that's where the ISO 5 comes into play. Then the next thing that happens is, and I've kind of shown it as just one thing, is that the receiver doing an IGMP, but think of the two things that we talked about earlier. That is, the two things that would happen is that the broadcast controller will do an API call to say start this flow, and that instruction will tell, first of all, do the bandwidth reservation, the resource reservation, which authorizes which flow, what's the bandwidth, and all, and what the quality of service is, and all of that stuff. And the second thing is it will also say whether the flow should be immediately routed or just wait for the receiver to ask for the flow. And then the second part of that instruction is that the receiver actually asks for the flow using IGMP, in which case that 2110 flow actually makes it to the receiver. There is one mistake, that the arrow should have been that side going into the receiver as opposed to coming into the switch.
So it can automatically detect how fast the network is, and whether you can, and then if it's not fast enough, does it automatically stop down the signal? Is that what it does?
There is not a speed thing here. The speeds and feeds are more connected to the capacity of the network and whether there is contention. So it is really speed of light plus the processing, that the speed of light for the distances of the cable, and then there is the processing, the minimum processing that actually happens. So if you're thinking about speed, it's the packet speed is based on how soon it actually gets to each switch and gets processed and plugged out of the next, out of its egress interface, out of its outside interface, so that it goes into the next hop. There is no slowing down or fastening that happens here. But in terms of what you may be referring to is capacity, bandwidth. So the thing is that when the broadcast controller does the flow, says please start a flow, the network does have an opportunity at that time, because resource reservation, and we say admission control, the admission control is, do I have the bandwidth? And there is always a possibility that no, you don't have the bandwidth. And in which case, at that point, you actually know at the broadcast controller this flow cannot happen because there is not enough bandwidth. Now, I mean, obviously, in a live production environment, that is not feasible. I mean, you don't expect to hear the word no, because you always want the bandwidth when you want it. So that is the reason why that securing that resources in that network is so critical. Because the thing is, when you do network design, when you're actually putting that network together on day zero, when you're actually laying this out and deciding how many switches to buy and whether it should have 10 gigabits interface or 40 gigabits interface, that's the time you're actually deciding whether that infrastructure has sufficient capacity for all the things you want to do in that production, in that environment. Now, after having set that up, then you expect that any request you make that is within that calculation will come back and say yes, because there is, I mean, you have already provided that resources, which is also why you don't want any of that to get stolen. You don't want any of that to get misused or reused for something else, and which is why that flow authorization, the whole protection and authorization that I talked about earlier becomes so critical. And the second thing is that, yes, there, in spite of all this, there is a possibility of saying no, and the reason is that there could be a link failure. There could be, there are, in an average, a leaf node will have, multiple connections to the spine node, like let's say 4 connections to the, let's say it's a 48 port switch, right? And that means you have 48 times 10 gigabits, that's 480 gigabits. But then on the top, you might have 100 gigabits links, so it might be 5 connections to the spine. Now, one of those links may go down, which means the capacity now dropped by 100 gigabits. Now, when you have those kind of situations, the first thing will happen is that's where the diagnostics and monitoring come into play, is that network controller, first of all, immediately tells the broadcast controller, look, my bandwidth got reduced. And the second thing it also does is if there were flows that are already in that link that was that has failed, it actually immediately tries to move it over to the other links that has capacity. Now, then the third line of defense is really where the SMPTE 2022-7 comes into play is that you have a network A and a network B, and if you really have failures in network A, these are the kind of failures you could have. But I know for Cisco I can speak, I'm sure other vendors do it as well, is that there are usually some failure handling mechanisms in the network so that it can kind of come back so that you're no longer left with just one network, but it comes back into two networks. But in the small period of time that it takes to resettle all of this and make it good again, that you are actually going to be relying on 2022-7 and the fact that you might be down by some amount of bandwidth between network A and network B.
This all sounds like latency issues.
Pardon?
It sounds like there's some kind of latency issues in all of this.
The latency itself, like I said, is the packet transmission, the processing time of packet transmission on any of these hops are in the range of actually it's in the ranges of nanoseconds, but maybe 2 microseconds. And this has been tested by Thomas Edwards. There is a big paper that he published in 2015, I believe, in SMPTE ATC, where he put us, he did the snake test, and he actually did a presentation which said something like IP is ready now, and this was in 2015. I do remember because I was sitting in his presentation. So there isn't, when we only have 2 hops, the latency frankly isn't much at all. And as long as the network design is done well and the bandwidth is sufficient, there is really no possibility of contention. This is for the broadcast. Every vendor, it's not only Cisco, but every vendor is providing a non-blocking fabric, which is why one of the critical things about this fabric is a non-blocking fabric. And we also call this kind of behavior, we call this a deterministic networking. And I just want to tell you that deterministic networking is not unique to broadcast in the sense that we have industrial automation wanting deterministic networking. We have broadcast and we have connected car. And I can tell you I've been working on pretty much a little bit of all of that. And in each case there is when I went to broadcast, they were like, oh, if you drop my packet, I'm going to lose millions of dollars. Okay, now more recently I'm working in connected car, and if you drop a packet, we could be having an accident and killing somebody. So you can see that the examples are, it is critical. That is why this word deterministic networking, because if you look back a decade ago, IP networking, or if you don't do deterministic networking, IP network is all about averages. Average 0%. Average 0% does not translate to guaranteed 0% loss, right? So deterministic networking. And for the industrial industrial Ethernet, the example that I always use is about Twinkies. Actually, I read this example somewhere, so it's not mine really. It's about Twinkies. You really don't want to buy a Twinkie that has all the sweet stuff smeared all over, right? You just want it clean inside, because you're not going to go pick that Twinkie if it's got all that sweet stuff all outside. Why? Because there is deterministic networking. Every machine has to operate in its time slice. So it's so yes, there are many industries that have placed a demand for deterministic networking, which is why many of our switches support PTP and other time protocols depending on which industry. And 0% loss, low latency are all part of the characteristics of a deterministic networking.
And that's network topology agnostic then?
Well, the reason I would hesitate to say that is because it's very much dependent on, like if you have a data center where you have a spine and leaf and you have a very controlled topologies, yes, deterministic networking is easy. But if you're looking at a branch or a campus network where you have branches and the packet hits, maybe that packet will hit 4 hops, this packet will hit 6 hops, then, your latency is maybe a little bit different, maybe in the matter of nanoseconds, but it might be a little different. In that case, deterministic networking is much harder. So I'm not saying that it's not there, but so depending on the kind of topology, in this case, in the broadcast space, it is data center topology, it's spine and leaf, so it's a very clean and a very easier type of network topology to do deterministic network.
With just a flat network as opposed to a spine leaf?
Yeah, if you have only one switch, or you just have 4 switches that every packet has to go through, then there's no difference really, right? We have found that we did some initial work when there could be a source and a destination device connected to the same leaf, as opposed to a source connected to one leaf and a destination connected to another leaf, which means it has to go through a spine. So obviously it's either 3 hops or it's the same hop, right? So we were trying to see whether there was enough of a difference in latency that was bothering the broadcast workflows, and whether we needed to take every flow, even if it was in the same switch, to just go to the spine and back just to get determinism. But we didn't, the vendors who worked with us at that time didn't feel the need to do that. They really felt that irrespective of it's 1 hop or 3 hops, the difference in time was so minimal that it really didn't matter much in terms of latencies. So I just have, you should go and look at jtnm.org for whatever the most recent copy is. There is always a recent copy of this. This is a JTNM roadmap. This might be an older version. Like I said, when I prepare these slides, they get, I take a copy of that. And the main thing I wanted to show here is not so much the timeline. Don't worry about the timeline. For the timeline, please go look at jtnm.org for the most recent. But I really wanted to focus on, look, there is a red area, an orange or a yellow area, and then there is a green area. We call it the red bit, yellow bit and the green bit. The red bit is all about transmitting media. So it is all about SIMT 2110, right? That is the content going from source to destination. It's about the elementary flows. And then there is this yellow bit, which is all about provisioning and what I call control and management, which is where ISO 4 and 5 and 6 fit in together, because that's the one that kind of makes provides that infrastructure for these flows to actually make its way from the source to the destination. Then there is the green bit, which has been, in work in progress. There has been a document that was published in time for NAB in 2018, and that is what we would call that was called the Agile Media Blueprint. But the main thing is that is where the virtualization and cloud and all of those comes in. So the word dematerialization really refers to the fact that you don't necessarily have a physical box, like it's not an appliance anymore. It's a piece of software, and therefore the software can live anywhere. Now, when you have an environment like that, what does a workflow need, and what orchestration do you need, what kind of capabilities you need? That is a very much an early stages of work right now in the standards in the AMWA organization. And even though a document was published in NAB, I would still consider that fairly early stages. So that is all the green bit. So I think I would, there was a lot of time I used to point to that yellow bit and say that's work in progress, because ISO 6 was in work in progress. But with August, with ISO 6 being published, I guess we are sort of done. And I mean, even though I say we are done, we still have a lot of other pieces of work that's happening. For example, there is work happening in this field of security. There's a little bit of work happening in with identity and identity workflow. So there are few grouping and things like that. So there's a little bit more work happening in that yellow area, but at least the original ISO 4, 5, 6 are sort of done. Okay. So really coming back to the final slide here, which is the AMWA ISO 6, and the whole idea about ISO 6 is really to have like a reliable network. You have a network that you can first of all secure, and then you have a network that you can actually get the services you need, which is in terms of sources and destinations. And by having an API, a common API, you no longer have to go to a vendor and say, okay, you are a broadcast vendor, but tell me which network vendor do you work with. It seems like a spreadsheet of match this vendor with that vendor kind of thing. Now, that is not necessary anymore, because you have an ISO 6. You can have any broadcast controller, or even multiple broadcast controllers who are operating with the same network, for example, and that is pretty much needed almost in all the environment, because you do have an audio. I mean, when we say broadcast controller, and I was using the example of GV Convergent, for example, that would would take care of the audio flows, and then maybe you would have another controller from another vendor for managing the audio side. So you do have multiple broadcast controller. They may be speaking to the same network controller. No longer do you have to say, oh, am I licensing that particular protocol from that particular vendor, because it is all quote-unquote standardized with ISO 6. So that means you can change your broadcast controller, operate with multiple broadcast controllers. And the main idea is securing the network, protect and reserve, right? You're protecting the network, you're reserving the bandwidth, and you're making the flows happen. That's ultimately the goals of ISO 6. Very simple goals. By the way, the one word that I think, except for once I did not use, but that reflects the ISO 6 is based on that, is actually ISO 6 is based on an SDN type architecture. And way back in 2014, when at my initial days of getting involved, when I looked at what the workflow looked like, I was thinking about how the video router was being managed by this broadcast controller. For me, it just said, oh, it seems like they need SDN. I mean, that's really what occurred to me at that point in time. And ever since then, been talking about how this architecture is that 3-layer architecture, or 2 layers, if you want to combine the network control and the network together. But the whole idea is it is somewhat an SDN or a centralized architecture where the broadcast controller is in charge of what happens in that network. So that's what my talk is all about. I hope it was useful and informative. Thank you.